All right, hi. This is my first recording in fall of 2023. Anything I've sent to you guys have been pre-recorded from last year or my teachings in summer semester, or during the review sessions, which we do have one on Tuesday. Or at least I do. If you're watching this in the future, sorry, I'm not there. Regardless, this is hopefully a more comprehensive video on most recent reactions, new things you should think of when you see these reactions. We should put on like potential flashcards. Hopefully, I'm gonna get to problem set 10 toward the end and just give you guys a better foundation for your final because it's gonna be a big one. In a good way. In a good way. Um, what else? I'm mainly doing this video largely because a lot of the ladies at 80 Pi were really begging me to the other night. Went to a day party. They were amazing crowd. I love them. So I had some free time, so why not? I can go ahead and do this. Before I start, I think a thing to note that I want to make is you guys have been working really hard, and I know that things are moving very fast. And unfortunately, OChem semester two is kind of a similar deal. When you get to spectroscopy and stuff like that, it kind of slows down a little bit. At least that was my perception, my perspective. But honestly, it's unique for everyone. And by the time semester two comes around, you actually are very used to pretty much everything. And that's why a lot of people find it easier, largely because well, you know what resonance structures are, you know how these reactions work, you know how to study for OChem. So as you move on to OChem 2, keep that in mind. If you have Berg, I'll see you again next semester. All right. Uh, with that in mind, I should probably go ahead and share. Actually, before I share my screen, I'm going to go ahead and share my laptop screen. So I'm going to make a little plug right here. You should be able to see it. But if you go to the files on Canvas and go to my notes, Magic Regular, right? You should see some of these PDFs, right? Some of you may have seen these, but this is probably my favorite one. This is a substitution and elimination chart that I made. Jackie's list is a lot more comprehensive, but it's also like, big out there. This one I think is a lot easier to digest. I use little fun colors. Um, we have our basic like methyl groups, primary, secondary, and I made sure to make note that there is a difference between my secondary for Zaitsev and Hoffman, because like right here on the top we have a secondary beta carbon. At the bottom we have a primary beta carbon. So there is a Zaitsev and Hoffman difference because there is radioselectivity. A thing to note, if you guys see this on the test, because some of you missed this on test 3, if your beta carbons are the same, like if you have two places to eliminate, but they're both like primary, right? There is no Zaitsev or Hoffman. There is no radioselectivity, so it's just E2. So that's something you guys should really make note of. And then I also add in the benzylic and allylic charts down here. Made a little note. Conjugation always trumps Zaitsev and Hoffman. Yeah. I think that file is a little too big for the supplementary notes right here in the middle, right over here. But if you scroll down to the bottom of that, I should have a comprehensive list of all the reactions that we've learned thus far, what they do. That's what I used to study. That's what I made when I studied for the final. You guys are welcome to use it. Use that as a template. Yeah, that's pretty much it. That's actually what I'm going to be working on right now, and then we'll probably work our way over to the problem set. All right. So let's go ahead and go on to here. There we go. All right, you guys should see this now. This is that list I'm talking about. So right here at the top, we notice, hey, look, we got our alkenes. These are our basic reactions that we started to learn at the beginning. And at the beginning, I mean test 2. You have our basic, hey, you have an alkene at HBr. So mark on the combination. It's like the back of your hands, but like the back of your hands right now. Carbocation intermediate. So we have hydride and methyl shifts, Markovnikov, nothing new. But we note that this is a Markovnikov, but something that you will see is HBr ROOR. Now, what does this mean? This is a peroxide. They can write it as ROOR or as literally, I cannot spell today, peroxide. They can also use that as a solvent because they're not very selective. But you might be asking, well, first off, what is a peroxide? Because I only heard that being thrown around in Gen Chem. Well, peroxide is just an oxygen-oxygen single bond. So hydrogen peroxide is this, right? This is that peroxide bond. It turns into a radical. It's a radical reaction. So that's what you write here, like, because technically CH3, oh, H, that could be a peroxide, right? Another peroxide you guys worked with was metachloropurbenzoic acid. It's a peroxide. It's a peroxy acid. It looks like this. Cl. Boom, boom, boom. Look, there's that peroxide. And that's what makes that epoxide product. Also make sure when you do the MCPBA, you show dashes and wedges. Always show that. But anyway, when you have HBr with a peroxide solvent, really easy. It's just anti-Markovnikov. BRH. That's it. It's anti-Markovnikov. I don't even know the mechanism for this, so I doubt you guys have to either. Oh, another thing to note is ozonolysis. So ozonolysis is a type of oxidation where you react a species with O3. If you do that, you basically just snip something down the double bond. I don't know if this is something you guys learned for test 3 or for the final. I forgot, so I'll play it safe. Just go ahead and talk about it right now. So if you have any kind of alkene, right, let's say you have cyclohexene and you react it with ozonolysis. I'm just going to put O3 for now, but you're usually going to have a solvent. You basically just take an imaginary pair of scissors and you just snip through there and you just make them into aldehydes. So a perfectly fine way of drawing that product is this. As you can see, I have my carbons, retention of carbons. Don't make sure you count your carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're just aldehydes. I'm just sticking oxygens between that imaginary snippet, right? And it's that easy. You don't have to know the mechanism for this either. We've reviewed creating alkynes with your frequently small strong base or using an SN2 reaction with an alkyne. Because if you remember, this is a weak base. It's a weak base. Some more alkyne reactions. Well, this is stuff that you've seen in test 2. Alkyne reacted to Br2. We get a bunch of BRs, a fuck ton of BRs. That's the scientific term, fuck ton. 2 HBRs, we get geminal dibromos. 2 portions of H2, not selective. It will just hydrogenate everything. But if you use Lindlar's catalyst, you create a syn addition. But if you solvate it with some kind of sodium or lithium metal with ammonia, you get an anti-addition of those H's. But it's only one reduction. It doesn't reduce everything. A very special thing to note are your ketones and aldehydes. If you have an internal alkyne, no matter what you react it with our HgSO4 or that BH3, we create a ketone. However, if it's terminal, if you react it with this terminal one with HgSO4, you create a ketone. But if you're to react with BH3, you create an aldehyde. Nothing new, something you guys learned. Just to review, we have our substitution elimination. And then we get to our big ones, removing alcohols, right? This is where we get some tricky stuff. So when removing alcohols, the main thing is to know, well, why do we want to remove an alcohol in the first place? Well, if you remember, an alcohol is an OH group. And if you know, OH minus is a small, strong base. It's a very bad leaving group. It wants to be on the nucleus of the carbon. It is a very strong nucleophile. So if we were to remove it, well, how can we remove it with, like, I don't know, a weak base, like a Cl minus, a chloride ion, or a bromide ion? How can you get a weaker base on there? Well, the main premise for most of these is just making the OH into a water. Water, when OH becomes water, it becomes very good leaving group. It might pop off spontaneously. If you add more reactants at the beginning, if you're doing this in a lab, you can push that forward reaction and increase the rate of popping off. Popping off. But that's the main logic behind it. But I know you guys aren't here for logic. You guys are here for some answers. And I get it. I won't bullshit you. All right. I apologize. For PX3 purity, this is just meant to represent any kind of halogen. This could be PCl3 or PBr3. Doesn't matter. But if you solvate it in pyridine, you get something like this. Whatever halogen you have. Let's say it was PCl3. I would do Cl, right? That's all I do. Reversal of your stereochemistry. The OH was left. The OH left, right? Now, for HX, this could just be whatever strong acid you use. This could be, not P, HCl or HBr, right? For this, you get two products. Same thing. If redox activity doesn't matter to you, you can use either this first one or the second one. It can either be away or retain that stereochemistry. You might be thinking, why is that? Right? Let me use an actual halogen here. Why is that? Let's do Br. Let's give bromine some love. Well, if we use a strong acid that it has a nucleophilic conjugate base, because if you look down here, we have another strong acid, H2SO4, but that conjugate base, HSO4 minus, is non-nucleophilic. So if we use a strong acid that does have a nucleophilic conjugate base, we get a different product. This is because, first off, the same premise. We use that strong acid to protonate that oxygen and make it water. If it's water, it'll pop off. And then this leftover nucleophile will add to wherever that carbocation is. And that's where we get no, not redox activity. We get no stereochemistry. Because remember, if you know carbocations, they have an empty p orbital. That nucleophile can add to either phase, stuff that you did learn in test 2. You can get either these stereoisomers. Now, what if you use a tosyl chloride, a tosylate, right? If you use a tosylate, TSCl, you will learn the structure, I think, in semester 2, or I think you'll revisit the structure because it's a benzene ring. I think it's on toluene, which is, yeah, CH3 on a benzene, some kind of toluene derivative. You make it a good leading group. So basically, what's special about this one that you definitely should memorize, because for this one, for these top 2, you can use either one of these. They'll get you that same outcome. But this one is less specific. This one will specifically make a leaving group that retains stereochemistry. So what do I mean by this? Well, hey, look, we have something like this. I'm going to put OT for that tosyl. All right, that's just an abbreviation, kind of like how we use ET for ethyl, right? OT retains the stereochemistry. And that might work in our favor if we're trying to do a special, if we're trying to be specific. And we'll see that when we get to the problem set. So if we use a large, strong base, again, this is an elimination of a good leaving group, of a good leaving group, while OH, remember, was that bad leaving group. Now if we have a good leaving group, large, strong base, that's going to be Hoffman elimination. It's going to look like this. If we had a small, strong base, we would do a Zaitsev elimination, something that looks like this. But2-ene versus but1-ene. Now, what if we get POCl3? Do not get this mixed up with PCl3. PCl3 is not the same as POCl3. They're different compounds, okay? These are different compounds. So for POCl3, we get an elimination. We get an elimination like this. This elimination is Zaitsev. This is going to be E2-like. E2-like Zaitsev. E2 Zaitsev-like, right? Don't overthink it. Do not overthink it. Just know E2 Zaitsev for POCl3, if your leaving group is going to be an OH. That's all you should think about. Okay. OH, bad leaving group, POCl3, I can eliminate it still with this special reagent. Now, H2SO4, same deal. You can use either one, same deal, right? You can use POCl3 or H2SO4. You get the same product. But this one is E1-like. So there are rearrangements. There's a carbocation intermediate. There's E1-like. And if it's E1-like, it doesn't have a choice to be Zaitsev. Because E1 is always Zaitsev, no matter what, because you have a carbocation intermediate. It has to be the most substituted direction, right? But regardless, don't overthink the difference. You can use either one of these. If you had a synthesis problem where you were eliminating OH, you can use either one of these and it would be correct, okay? Some of you might be questioning, well, there might be errors in the final, kind of like how we had the errors, not the errors, but like some miscalculations on some of the midterm exams. Like people came up to us like, hey, this was miscounted wrong. I am missing 2 points. We'll give you the 2 points back because we do it on paper. For the final, we grade it essentially twice. So don't worry about that. There is like a backtracking to make sure everything's accurate, okay? Okay, let's move on to organometallics. Grignard just basically breaks a carbon-oxygen double bond. We're gonna play more with it later on. Let's not half-ass it. Let's go ahead and make some examples. But essentially, what you'll be doing is you're making a carb anion. So a very strong nucleophile is gonna be like OH minus or NH2 minus, right? Small strong base, frequently small strong base. Well, CH3 minus, a carb anion, is a very strong base. Because the pKa of methane is going to be like 50. So if you remove a proton, it wants that proton back because it is not very acidic. If you pop that proton off on something that's not very acidic, it's going to be very strong. And then this makes sense, right? Because if you remember like Gen Chem, right? You have a hydrophobic tail and a hydrophilic OH head that can make hydrogen bonds. Well, that's pretty acidic. It's polar. But that hydrocarbon tail is going to be very nonpolar. Those protons are not going to pop off. So if you somehow rip off that proton, it's going to want that proton back. And you do this with MGBR. So the general flow is if you have something that's a BR, let's say bromopropane. You react it with Mg, magnesium, with dry ether. The polarity of the ether will stabilize the bonding of magnesium into that carbon-bromine bond. All right, it'll do that. It's also not acidic enough. It won't interfere with the reaction. So that's why we like to do it with dry ether. But we get something like this, MgBr. Another way to write this is this. This is an ionic bond. Or that's how I imagine it, ionic bond. We still draw them together. We draw it like this. We draw it like this, right? I'm going to highlight this. This is how we normally draw that Grignard reagent, right? We draw it like this. But what I drew down here is how I like to think of it because it highlights the carb anion, what carbon is going to attach to that carbon-oxygen bond. So if I were to treat this with, let's do a ketone, right? Your carb anion, see, this is why I like to draw it that way. We'll come over here, pop that over. We treat it with an H plus catalyst. So like, let's say HCl, we get something like this. It looks like a little man. I did not expect that. It's pretty cool. We get something like this. We get a 1, 2, 3, 1,1,2 trimethyl propanol. Yeah, something like this. If we were to react it with an epoxide, still we have a carbon-oxygen bond, right? Carbon-oxygen bond. We react it with our Grignard reagent, right? Let's draw it. This is another way you can draw it. If you're trying to make a synthesis and use the Grignard reagent, you're welcome to do this. For the H plus catalyst, the strong acid, you can use HCl, or you can just put H plus cat Perfectly fine. Well, whatever nucleophile you had would pop that open. Electrons would go here. This is that intermediate. Oh, want to highlight this and this carbon are these two original carbons. Oh, oops. I drew that wrong. My bad, you guys. My bad. There we go. Sorry, I drew that wrong. That's my bad. Um, and then again, remember that H plus catalyst right here. We protonate it. There you go. That's the product you get. You basically open up a carbon-oxygen bond. A neat trick that you can do with Grignard reagents when it comes to semester 2 is you can make a carboxylic acid. Because if you have carbon, oxygen, right? The most oxidized form of carbon, well, it is chock full of carbon-oxygen bonds. So if you had that Grignard reagent, let me redraw it here. Right? If you were to have this attack right here, open this up, you get something like this. Then we have that H plus catalyst. We get a structure that would look like this. I'm going to redraw it just so it's a little more condensed, or it looks a lot nicer. Look, we have a carboxylic acid. So if you react your Grignard with CO2, you get a carboxylic acid. Just a neat thing. Play around with it. You don't have to know it too in depth. You can just know what it does. Honestly, this is probably the extent you should know about it. I'm just trying to show you some cool things that you can do if you want to like just think more on it. This is not the expectation. Don't worry. All right. So some other organometallics, the cuprates, the organocuprates. So the organocuprates is a little broken. Whatever is in the parentheses right here is what you're replacing on that bromine. That's what I like to think. So whatever's in the parentheses, you pop and replace that bromine. So I have CH3, CH3. I think that'd be CH2. I think I wrote it wrong in the thing, but regardless, ignore it. Whatever's in the parentheses, you put here. So there was a Br there before. Now just putting an ethyl group there. You can do the same thing with Suzuki coupling right here. Whatever that ligand the boron is attached to, that's what you're replacing with the Br. Now, what makes these special is you can use it on an sp2 hybridized carbon. Right here, look. That carbon is sp2. It is attached to Br. If you were to react it with any kind of substitution elimination, it would not work. It's sp2 hybridized. It would not release that that bromine. But for this situation, it can. So it's a cool thing to make note of. Something very special are plain alkanes and alkenes. So this is probably one of the most important reactions to learn or pick up from this problem set. If you have a plain alkane, you're trying to get functional groups on it, you need a leaving group on it first. So if you use Br2, H nu is supposed to represent light, delta is supposed to represent heat. So heat, delta, it's a very common way to signify you're heating it up, like you would in a Diels-Alder. For Diels-Alder, you would just heat it up, and they just put a delta in that arrow. In actual lab, you can just react a bromine with whatever organic compound you have, shed some light in it or heat it up. You'll get the same thing, but that's beyond the point. Just Br H nu or Br delta, that'll work. But it basically just slaps a bromine on the most substituted carbon. Let me show you what I mean by that. If you had something like this, and you're trying to, let's say, make it to something like this, how can we do that? We don't have any functional groups on this left alkane to do anything with. So the most common first step for a lot of synthesis is Br2H nu. So if we use Br2H nu, just put the delta for consistency, we get something like this, the most substituted carbon. And then we can just eliminate it. We can just do NaOH. Small strong base, eliminated Zaitsev. Boom, bam, done. NBS does something a little similar. It adds bromine to an allylic or benzylic carbon. So we have an alkene right here. This is our double bond. This carbon is allylic. This carbon is allylic. So if we have NBS, we can add a bromine to something allylic. And we do end up getting that. Yeah. This is another chart I might have redrawn. This might have come straight from the notes. I remember drawing it, I think, Friday morning. Just little comprehensive chart. Mild oxidizer. The easiest one that I know is PCC. I don't have to like draw out acetic acid and bleach. I just put PCC. Same thing with strong oxidizer. Just H2SO4 works. Ooh, something to note. Some other ways strong oxidizers can be written is K2CrO4, another way, or they can use manganese, H2MnO4. Strong oxidizer. Okay. Yeah. For some ethers, these are just some things that we have looked at, but actually, no, we have not looked at most of these. I lied. The first one we have seen, the first one is showing just in SN2. We have a primary leaving group, bromine, and we have a small strong base. It's going to be ethoxide. So we just SN2 and we get something that looks like this. SN2. That's one way you can make an ether. Another way you can make an ether is with this, right? So if we have, let's say, an epoxide, which is something that you guys have seen in the problem set. If we have a base that is acid catalyzed, so acid catalyzed base, the ether goes on the most substituted carbon right here. So let's make it real clear. Both of these two are identical. I'm going to call this one the most substituted. Most substituted. This is the least substituted. Least substituted. So when it's acid catalyzed, the OCH3 goes on the most substituted. It is SN1-like. It's Markovnikov. And obviously you have a rate of reactivity, right? Tertiary reacts a lot faster. Then you also have secondary and primary also reacting a lot, following in reactivity. So what essentially happens is when it's acid catalyzed, we protonate that oxygen. This will pop off. And you will be left with a carbocation right here. And that's where the nucleophile will add. But for here, if it's base promoted, it'll be the complete opposite. The OH will be on the most substituted. The methoxide or ether will be on the less substituted. As SN2-like addition, primary, it's a lot more reactive than secondary. Don't overthink it. Yeah. For the diols, these are our last two that I want to make note of. If you use osmium down here, osmium with 4 oxygens, you can create a cis diol system. If you use NaOH, H2O, HCl, you create a trans diol system. Yeah. That's kind of it. All right. Let's stop that share. I'm going to pause the recording real quick, and then I'm going to download the problem sets. Okay. Pause it. All right, I'm back. All right, I have it downloaded. I'm going to try my hardest not to straight up give you guys the answer. I'll give you guys hints or draw out what you need to know to answer it. Or I might just straight up give you the answer. We'll see how I do. Let's share the screen to the iPad. It is loading. There we go. All right, there you go. Let me move my feed. Okay. Nope, that's not it. There we go. Okay, let's put on old glasses. We'll pull a Dr. Berg. Okay, sweet. Okay, well, let's take a look. SOCl2. All right, for SOCl2, that's pretty easy. SOCl2 just replaces. Actually, I don't think I covered this early in my notes. Oops. Well, good thing I'm telling you guys now. SOCl2, you react with pyridine. I think this goes back to that first reaction. Actually, I may have covered it. PCl3, PCl2, SOCl2. Is that this? They don't play. No, 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 no. Hold on. I'm tripping. I'm sorry, you guys. I'm so sorry. I know I didn't cover it, but this is something that he did cover. Yeah, this is a phosgene. Yeah, this is hella toxic. This is a chemical warfare agent. I forgot about that. Yeah, this will destroy and tear up your lungs if you deal with it. Yeah, we don't usually work with this in lab, but it is really good at replacing OH. I'm so stupid. I'm so sorry. Um, yeah, you solvate it in a pyridine, and you basically replace an OH with a Cl2, right? So if you replace the OH with a Cl2, that's exactly what it means. Cross out the OH, erase the OH, and just put a Cl2. Let me give you an example. So SOCl2 is very special because on top of sp3 hybridized OH groups, it can replace an OH group on an sp2 hybridized carbon. So if you have something like this, OH, right? That's just acetic acid. You treat it with SOCl2, pyridine, you get something like this. That OH is just replaced with a Cl. Something very handy for you guys to learn test 1, semester 2. To give you another example, it can also work on, let's not delve into that. Let's just make a little example. Something like this, OH, SOCl2, pyridine. That's it. Yeah, good chunk. That's the main one. Yeah, I don't think I'm gonna give you the straight up answer for this. I'm just telling you, it just replaces the OH with a Cl. Don't overthink it. Now, take a look at this. We have a strong oxidizer. Strong oxidizer. We have a strong oxidizer. Let's analyze the OH. This is a primary OH. You guys are still troubled by that? Well, I'm sorry. If it was tertiary, it would be no reaction because that carbon needs to have a hydrogen in order to be, that has to be released in order to be oxidized. So if we have a primary strong oxidizer, we create a carboxylic acid. This is in the chart in the notes, or earlier in the video if you saw or paid attention and didn't skip. Who's texting me? My mom is calling me. I'll call her back later. Count your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Make sure you count your carbons. Okay. This does not cleave or create any carbon-carbon bonds. It just creates more carbon-oxygen bonds. You create an alcohol into a carboxylic acid. For here, look, we have an epoxide. We have a weak base that is acid catalyzed. Acid catalyzed. Well, we know we're going to protonate this oxygen. We're going to pop it off. CH3, CH3. Maybe we can keep it consistent. Nah, I'm not going to do dashes and wedges. Never mind. CH2, OH, carbocation. Right here, this is the H that we added from that acid catalyst. So now we have OCH3. That OCH3 will be a nucleophile and attack there. You're going to get something like this. I'm going to draw it down here for simplicity's sake. Positive sign, CH3. And as you know, if you have been memorizing or studying that mechanism you learned in test 2, that H will just be popped off by methanol in your solvent, and then the protons will just pop back here. Yeah, that's pretty much it. So I'll let you guys finish that, but I showed you what's adding where. Here's a fun one. SOCl2, pyridine, and then NaCN. You might be thinking, well, isn't this the same as this? Answer is no. The second step might be the same. The second step is showing you an SN2, right? An SN2. So the first step is basically trying to differentiate it. For this one, you don't retain stereochemistry. For this one, you do retain stereochemistry. So let's go ahead and do this first step for both of them. CH3. OH is our leaving group. SOCl2 does not retain stereochemistry. We get Cl. First step for here. CH3. Our tosyl chlorate does retain stereochemistry. So it's going to look like this. Now let's go into the second step. The second step is going to be in SN2. SN2, what are our good leaving groups? Well, our leaving groups are Cl on the top and OT at the bottom. So if we did an SN2, we would do a complete reversal of stereochemistry. Backside attack. CH3, CN. Here, our backside attack would keep it as wedged. There you go. All right. For osmium, you know that osmium will create a diol. These diols will be cis to each other. I'm just adding two OHs across the alkene. Now you can draw both of these diols as wedged and have, or both these alcohols as dashes and have this methyl group be wedged. That's fine. As long as they're cis to each other, we'll accept either one. HBr peroxide. This can also be drawn as ORR, ROOR. It's a peroxide. Remember, HBr is Markovnikov addition of Br and H. But if it is under peroxide conditions, it is adding HBr anti-Markovnikov anti-Markovnikov addition. CH2. You have secondary, primary. Normally the Br would go on the secondary, but since it's anti-Mark, it would go on the primary. NBS. NBS adds a Br to an allylic or benzylic carbon. Your allylic carbons, well, let's take a look at our alkene heads. These are alkene carbons. They are sp2 hybridized. This is allylic, this is allylic, meaning they are right next to the alkene. All right, right here we have cuprate. We're going to be creating a butyl lithium, not butyl lithium, but that's what you were taught in the notes. You create a butyl lithium, kind of like the MgBr in Grignard reagent creates a nucleophile, nucleophilic carbon. You essentially do these first two steps. You create your cuprate. This is how I'm going to draw it. Cuprate. You have a cyclopentane complex with copper and lithium. And then this is the doozy, 3CH3Br. Whatever leaving group you have, you just replace whatever's in the parentheses into that system. You just replace it. This one is also a little tricky. All right. This, you might be thinking, well, what the heck is this? Well, this is a little tricky because this and this is your Suzuki coupling reagents. All right. That's all you needed. This right here in the reaction arrow, that's just the solvent or the reagents that the Suzuki coupling uses. But this is the actual ligand that they are focusing on. Whatever that boron is attached to will be attached onto that leaving group. So basically, all you're doing is trading that Br with whatever group is attached to the boron. All right. So to give you an example, if your ligand is like CH3CH2 boron, and let's say that ligand complex was this, a lot similar to the one that we showed you in class and in my notes. But again, whatever that boron is attached to, it's like attaching itself to wherever that Br is. The Br is going to leave, and that CH3CH2 is going to add. That's the logic you should be following to complete this bottom right one. I usually kind of think of it as like a pair of like tongs, like a two-armed tong, whatever's in the tong you're trying to like place in there. And my arms are like the ligands. I know it's a little immature to imagine that way, but that's how I do it. My tongs are going to be right here, that boron complex. The tong is attached to that ethyl group that's going to replace whatever is attached to that bromine. Right. HeOCl3. HeOCl3, if you remember it, or if you looked at the beginning of the video, is going to be an E2-like elimination. E2 Zaitsev-like elimination. So this will leave, we get an elimination. If it was PCl3, it would be a substitution. Something like this. Yeah. If you want to be more accurate, you can probably draw it like this. That works. For H2SO4, that's going to be another elimination that's E1-like. If it's E1-like, it has to be Zaitsev. This is our alpha carbon, beta, beta. Out of our two betas, which one is more substituted? This one is more substituted. Whoops. It's more substituted. So CH3, CH2, CH, C, H3. There you go. That is an E1-like elimination. HBr. You have a substitution, right? Normally, your gut might be telling you that's going to be something like this, right? Because what you're essentially trying to do here, let me just show you. This H is going to add onto this oxygen, making a good leaving group. This oxygen will just completely pop off, leaving you with this carbocation. And then you might be thinking, then the bromine adds. Well, this is the tricky thing. There's a carbocation shift. Again, carbocations are susceptible to shift. So in actuality, that carbocation intermediate is going to pretty much exist as this one instead. And that carbocation will be where that bromine will be attaching itself. All right, next one. We have a mild oxidizer. This is bleach. This is acetic acid. Bleach, acetic acid, cold temperature, because oxidation reactions are very exothermic. You oxidize it. So this is secondary. Secondary with a mild oxidizer, you get a ketone. Secondary, if you use a strong oxidizer, you also get a ketone. Here, you can draw like this. Oops. There you go. It's a ketone. Here, look. We have that same epoxide we saw in group 1, but we have a base that is base promoted. So you have your most substituted, you have your least substituted. Your most substituted will have the OH. Your least substituted will have your OCH3. And you're adding OH and you're adding OCH3. Which one goes where? If it's base promoted, OH is on the most substituted. If it's acid catalyzed, OCH3 is on the most substituted. Look, we have the cuprate again. Again, whatever's in those parentheses, you just replace that. The bromine just pops off, and that's where you whatever's in the parentheses you add on to. You literally just copy and paste CH3, C, what's next to me? CH, oops. This is what I added and replaced. Look, Br2H new. You have an alkane. You have an alkane. What can you do? Well, Br2H new just adds a bromine to the most substituted carbon. Let's look at it. Most substituted. We have primary, primary, primary. We have secondary, but we do have one tertiary. That is where that bromine is going to add. There you go. If this was delta instead, that's a very bad delta. Hold on. That was delta instead. Same thing. Either one. NBS adds bromine to a benzylic or allylic carbon. This is your benzene ring right here. The carbon next to it's benzylic. That's where it'll add. And same thing over here. We have our tosyl chlorate and PCl, and then we have an elimination. Before we saw substitution, but for this one, see an elimination right here. Let me show you what I'm talking about. First step, you make the OH into a good leaving group. The second step, you're making an elimination. So let's make this first step. So the tosyl chlorate will create a leaving group in the same stereochemistry. Retain the stereochemistry. PCl3 will not. That leaving group, oh, I don't know why I wrote Cl. It's supposed to be OT. My bad. My bad. Cl, CH3, H. All right. Second step, we eliminate it. This is going to be an E2 elimination. E2 elimination, small string base, is going to be Zaitsev. All right. But if it's E2, it doesn't matter if it's Zaitsev or Hoffman, that beta hydrogen has to be anti-periplanar. So for this one, whoops, this is your leaving group, dashed. This is your alpha carbon. Oh, not your alpha carbon. Those are the beta carbons. Beta, beta. Beta 1 is more substituted. Beta 2 is less substituted. You might be thinking, let's go to beta 1 up top and make that double bond. You would want to make that double bond right here. That's not the case, because that H that would be leaving is not anti-periplanar. So that double bond has to form here. Here. Let me show you what I'm talking about. If this leaving group is dashed, this is the only hydrogen that can leave because it is the only one that's wedged. But for here, let's redraw our hydrogens. This is your leaving group, right? Yes, we'll do E2. The hydrogen that has to leave has to be on an anti-periplanar beta carbon. This hydrogen can leave, this hydrogen can leave because they're anti-periplanar. This one is Zaitsev. This one is Hoffman. That should be it. All right, I'm gonna stop my share. You can tell that actually got a little darker. Not so much time to spend on it. Yeah. Anyway, this should pretty much help you with all of your organometallic reactions and your problem set 10. You want to thank me, bring me Starbucks on Monday. You don't have to. You're welcome to.